Okay, the quiz is now too late to submit, so I can go over it now. Of course, I'll say something quickly about quizzes also. Some of you already noticed this, especially if you submit quizzes early. If you submit the quiz early enough, like if you submit it Friday, I can usually get to it by Saturday. If you submit it Saturday, I can usually get to it by Sunday. But sometimes if you submit your quiz early enough, now of course I don't want you to rush through it, but nobody's really doing that. But sometimes if there's something that's not right, if you submit it early enough, I can tell you, hey, fix this or try this or this is not quite right, and you still have a chance to resubmit it. Okay, now, if you just submitted the quiz, let's say some of you just submitted it 15 minutes ago, then obviously I don't have time to look at it, then it's just one shot, it's a one-shot deal, right? But if you submit your quiz early, I usually try to get it within, the next day. Sometimes if I just happen to log on and you submitted it just a few minutes ago, I can answer right away. But let's say if you submit the quiz on Friday, I can usually get to it by Saturday, maybe earlier. Or if you submit it Saturday, I can get to it by Sunday. And if you submit it Sunday, maybe I can get to it by Monday morning. And then if something isn't quite right, I have a chance to tell you and say, okay, maybe you can fix it before class starts, and that's acceptable. I'm not promising you I can do that all the time. If I get inundated with a whole bunch of emails, I may not be able to get to it. So I'm not promising you that I will be able to do that for you, but I'll try whenever possible to do that for you. Okay, anyway. Number one, pretty much nobody had any trouble with that. So 6x minus 5, that's it. For 2, you need to set this up first as 2x to the 1/2 minus x to the minus 2. Okay, so then you can use your rules. The derivative of 7e to the x is itself. Derivative of this becomes x minus x to the negative 1/2. And this becomes a positive 2x to the minus 3. Now, you're not supposed to leave an answer like this. Okay, so never leave your answer with negative exponents unless the problem starts off with negative exponents. And the other exception is if you have an e. If there's an e involved, like e to the negative x, you can leave it as e to the negative x. Also, since the problem started off with a square root, you should not leave your answer with a 1/2 exponent. So best final answer, 7e to the x minus 1 over radical x plus 2 over x cubed. Okay, number 3, product rule. First times the derivative of the second plus the second times the derivative of the first. You could leave it like that. Some of you went ahead and factored. If you factored, that's okay. I don't mind, but the main thing is I want you to be able to show me the product rule. So this was acceptable. 4, however, you should keep going with the numerator because it cleans up. Okay, so anyway, bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Normally, it's not necessary to multiply out the denominators. If you went ahead and did it, that's fine. You get some super big numbers. Usually the denominator, just leave it alone. But the top, you get the cancellation of the x's. So best final answer is 98 over 5x plus 16 squared. Okay, 5, recurring theme. Find the equation with a tangent line. So take the derivative, plug in 0. So derivative is 4e to the x. Plug in 0, you get 4. Then do your y minus y1 equals m times x minus x1. You could leave it like that, or you can tell obviously that y equals 4x also works. Okay, so there we go. I will also mention, I tend to grade much more liberally on quizzes than I do exams. Okay, so a lot of times I'll let quizzes go by. I try to make the quizzes very low pressure. I might excuse quote unquote small mistakes, but I may not be as nice on major exams. Okay, so whereas I may have let some things slip by on quizzes, I may not be as willing to let that slip by on major exams. Okay, so just thought I'd let you know that. Okay, so we're continuing on up to here. So 3.4. Now, my game plan for today was to stop after a certain while and then let you ask questions, okay, because some of you may have had some questions about earlier material. Okay, so I won't lecture the whole time. I rarely do anyway. So I'll stop after a while. So think of any questions you might have on 3.1, 3.2, 3.3. And then if nobody has a question, then we can just stop and we're done. Okay, but I gave you the chain rule last time that helped me out because now that you've seen it, I'll just get started with doing some of the problems with that. and I'll do a little bit more tomorrow, and then we'll go on to 3.5. Okay, so we're still looking at quizzes for Fridays for now. We're not aiming for the next exam to be until what looks like Friday the 23rd. Okay, and again, this is our longest chapter, as you can see, is 11 sections. Okay, and chapter 4 and chapter 5. Well, chapter 4, we're skipping what, 4.6, and as I mentioned before, 4.9 I'm including with chapter 5 because that's where I think it really belongs. Okay, so I'll lecture for a while, but I'll stop after a certain while and let you ask. So think of any questions you might have on previous stuff, 3.1, 3.2, 3.3. All right. Okay, so we're back to the chain rule. So new derivative is the chain rule. And it's how to differentiate a composition of functions. Okay, so page 198. Okay, so in the Leibniz notation, dy dx is dy du times du dx. Okay, when you have a composition like this, it's f prime of g of x times g prime of x. So you take the derivative of the outside function first with respect to the inside function, and then times the derivative of the inside function. Okay. And they've got it again here. F circle g, the composition of functions f of g of x. Okay, so f prime of g of x times g prime of x. Okay, now I showed you an example of this last time, but page 200. How do you like that? We've already got 200 pages of calculus under your belt. Okay, but the power rule combined with the chain rule looks like this. The derivative with respect to x of g of x raised to the n power. Okay, so it looks like the power rule, but it's not just x to the n, it's a function to the n. So you go n, g of x raised to the n minus 1, so that looks like the usual. But now the chain rule says it's times the derivative of the inside function, so it's times g prime of x. Okay, so one more time, blah, blah, blah to the n power. N comes down in front, g of x to the n minus 1, that looks like the power rule as before. But now the chain rule says it's times the derivative of the inside. So you have to take g prime of x. Okay. And I'm going to show you this example on page 201. Okay, y equals x cubed minus 1 to the 100th power. Okay, so you start off with 100, x cubed minus 1 to the 99th power, and it's times the derivative of the inside function. So it's times 3x squared. And then a little bit of cleanup. 3x squared times 100 is 300. 300 x squared times x cubed minus 1 to the 99th power. Obviously, you don't want to do any more with x cubed minus 1 to the 99th power. There's no way you or I or anybody feels like multiplying that all out. So just stop right over there. Okay. All right, so we're ready to do some 3.4 exercises. Okay, so again, what are we supposed to do? 3.4, it's like 7 to 53, odd, 61, 65. Okay, so page 204. Okay, so here are some problems for those of you that aren't getting the book and you just want to piggyback off what I have. Okay, and then a little bit more toward the bottom. And then let's see. Do we have to do anything on the next page? We're going up to what, 65. So yeah, unfortunately, I got to give you stuff here too. All right, so there's some there. And there's the bottom part. And okay. All right, so practice with the chain rule now. Okay, so 3.4, how about number 7? Show you that one here. So 5x to the 6th plus 2x cubed raised to the 4th power. Okay, so the outside function is raising something to the 4th power. The inside function is this mess. So it starts off like you expect it to. 4 comes down, copy the blah, blah, blah raised to the 3rd power. 5x to the 6th plus 2x cubed to the 3rd power. Now the new stuff, it's times the derivative of the inside function. So now I differentiate that, and that looks like 30x to the 5th plus 6x squared. And yeah, you could just stop right there. There's no reason to go any farther with that. The only little thing you might want to do is multiply this by 4, but in this case, you don't have to. So if you do it, that's fine. If you don't do it, that's fine. Definitely, you don't want to multiply that out. That's no fun, raising this to the 3rd power. Okay, number 11. F of theta equals cosine of theta squared. And I want you to notice this is not the same as cosine squared of theta. Cosine theta squared, by order of operations, this means theta times theta first. And then you want the cosine of the whole thing. Okay, if the 2 were here, where it says cosine squared theta, that means cosine theta times cosine theta. Okay, that's like cosine theta parentheses squared. Okay, so in other words, when it's like this, the outside function is the cosine function. The inside function is theta squared. Okay, so ultimately, I like to cover things up sometimes. The outside function is cosine. So how do you differentiate cosine? Negative sine. So it starts off with negative sine theta squared. And now by the chain rule, it's times the derivative of theta squared. So it's times 2 theta. Okay, and that's pretty much about it, except normally when you have a polynomial and a trig function, you put the polynomial in front. So negative 2 theta sine of theta squared. Okay, and I'll say something else. You normally don't want to leave an answer like that because this could be ambiguous. When you write it like this, right, somebody might interpret that as saying, oh, should I do theta squared times 2 theta first? In other words, find negative sine of 2 theta cubed, right? That could be interpreted that way. But if you put it in front, right, then now nobody's going to think of it that way, right? Nobody's going to think that it's 2 theta times theta squared because there's a sign like this. Right? So this very clearly means negative 2 theta times the sine of theta squared. So to avoid that confusion, to avoid the ambiguity, right? See, when you leave it like this, you wonder, does it mean this or does it mean I multiply this first and then I take the sine of all that? So this avoids all confusion. Okay, so that's that. All right, next one I want to show you is y equals x squared e to the negative 3x. All right, so this has a product rule. There's also a chain rule for e to the x. It's not just e to the x, actually. It's e to a function of x. Okay, so the outside function, as far as this is concerned, is e, and then there is an inside function, which I have to differentiate. All right, so product rule. This is my first function. This is my second function. Right, so first times the derivative of second. So what's the derivative of e to the negative 3x? So first you put e to the negative 3x, and then by the chain rule, it's times the derivative of the inside function. The inside function is negative 3x. The derivative of negative 3x is negative 3. Okay. Plus, still part of the product rule, second function, e to the negative 3x, times the derivative of first. So the derivative of x squared is 2x. Okay, that's essentially it except for cleaning up the algebra. So best way to write it is negative 3x squared, e to the negative 3x. And then once again, normally if you have a polynomial and an exponential, put the polynomial first. So plus 2x e to the negative 3x. Okay, so again, there's a product rule and a chain rule. First function, second function. First times the derivative of the second. So the derivative of e to the negative 3x is e to the negative 3x times negative 3. Negative 3 is the derivative of negative 3x. Plus second function, e to the negative 3x, times the derivative of the first. Derivative of x squared is 2x. Okay, this problem is finished, but I'm going to dig a little bit deeper. How do you differentiate e to the x squared now? Okay, so it's not just e to the x, it's e to a function. Right? So the outside function is exponential. So first you just copy the original. The derivative of e to the x squared is e to the x squared. Then by the chain rule, it's times the derivative of x squared, which is 2x. And I'll write it as 2x e to the x squared. All right, now with that in mind, I can now show you a derivation of how to differentiate any other exponential function besides e. So we know the derivative of e to the x is e to the x. How about what's the derivative now of 2 to the x, or 10 to the x, or pi to the x, or any other base to the x power? Okay, so to motivate that, it's part of the chain rule, and the book goes over a derivation of this. So before I show you how that works, let me go back and show you in the text of what to do. Okay, so I'm on page 202. Suppose we have any base b. I want to take the derivative of b to the x. Yeah, they got the answer right here. But here's the trick. Not sure you can see this. B to the x, you can write it as base e. It's e to the ln b raised to the x power. Okay, this thing right here, e to the ln b, is the same as b. Okay, one of the properties of logs is if you have an e and an ln next to each other, they can cancel out. So it's the same as b. So this thing inside the parentheses on page 202, I claim that's equal to b, e to the ln b, right? That's b to the x power. And now if you have a power of a power, you can multiply the powers. So it's e to the ln b times x. And now I got it to be base e, which means I can now do the chain rule. The derivative of b to the x is the same as the derivative of e to the ln b x. Now that I've written as base e, the derivative is the same thing, e to the ln b of x, and then times the derivative of the exponent. Okay. What's the derivative of ln b x? Well, ln b is a constant. So it's just like asking what's the derivative of 7x? 7. What's the derivative of negative 3x? Negative 3. So what's the derivative of ln b x? ln b. So I have e to the ln b x times ln b, or b to the x ln b. All right, so now we have our new rule. Okay, and again, if you want to put this in your cheat sheet, you may. The derivative with respect to x of b to the x is b to the x ln b. Clearly not as nice as e to the x. So what's the derivative of 2 to the x? 2 to the x ln 2. What's the derivative of 10 to the x? 10 to the x ln 10. So you have to put that ln every time. In case you're wondering, does that work for e? It also works for e. If you just follow this rule, you would have e to the x derivative is e to the x ln e, but ln e is 1, so it works fine. Okay, so you get what you want. Okay, so let me lose the text now. Now, if you couldn't see what I had in the text in the book, I did my own derivation with base 2. What's the derivative with respect to x of 2 to the x? Okay, so the trick is to write 2 as e to the ln 2. And by the way, this is only for the derivation purposes. You don't have to run through this every time. You can just go straight to the shortcut. Okay, but if you want to prove it, write it as base e. See, I claim this is still 2, right? E to the ln 2 is still 2. So it's still the same as 2 to the x. And then we have a property that says if you have a power of a power, you can multiply the 2. So e to the x ln 2. ln 2, you can punch it in your calculator. It's like 0.693. And now I've written it as base e. So the derivative is the same thing, e to the x ln 2. And then by the chain rule, times the derivative of all this stuff, which is ln 2. But we might as well write this back as the way it originally was. What was that originally? 2 to the x. So 2 to the x ln 2. Right. So summarizing again, the derivative of 2 to the x is 2 to the x ln 2. Derivative of a to the x in general is a to the x ln a. Okay. So the derivative of 1,000,000 to the x is 1,000,000 to the x times natural log of 1,000,000. Okay. So clearly it's not as nice as base e to the x. Okay. All right, so we're going to do a few more here. How about I'll show you 15. E to the at sine of bt. Now, they write it as f of t. That tells me t is the only variable. A and b are not variables, they are constants. Okay, so there's a lot of things going on here. There's a product rule. There's also a chain rule where A is a constant and B is a constant. All right, so here we go. Product rule. First function times the derivative of the second. So derivative of sine of bt, cosine bt, and now by the chain rule, it's times the derivative of bt. Okay, I know you see a bunch of letters, but you have to treat b as a constant. Okay, so like what's the derivative of 5t? 5. What's the derivative of negative 19t? Negative 19. So what's the derivative of bt? B. Plus second function, sine of bt, times the derivative of the first. So what's the derivative of e to the at? Same thing, e to the at. And then by the chain rule, it's times the derivative of at, which is a. Okay, this is essentially it. All I was saying is that to finally clean it up, I'm just going to say, etc. You can do that. But normally you would put the b in front, and you would normally put the a in front. I didn't feel like doing that. You can do that on your own if you wish. In fact, I should be stronger. You should do that again to avoid the ambiguity. But all you do is put the b in front and put the a in front. Okay, so one more time. It's a product rule. Here's the first function. Here's the second function. So copy the first function, then times the derivative of the second function. Derivative of sine of whatever is cosine whatever. And then by the chain rule times the derivative of bt, which is b. Plus second function, copy it, sine of bt, times the derivative of the first. So what's the derivative of e to the at? Same thing, e to the at times the derivative of at, which is a. Okay. Okay, 25 looks like it's going to be a pretty bad one. It's not just x to the 8th, it's a big mess to the 8th power. Okay, so the outside function is raising something to the 8th. Whoops, I didn't want that. So you go 8, blah, 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 raised to the 7th power. Okay, so that's quote unquote normal. 8 times all this stuff to the 7th. And now the chain rule says it's times the derivative of the inside. Okay, but the inside is a quotient root. Okay, so I'm finished with this stuff. I'm finished with 8, u cubed minus 1 over u cubed plus 1 raised to the 7th power. And now times the derivative of all this stuff. Okay, that's a mistake there. Never mind about that. So now I focus my attention on just this. Okay, so bottom, u cubed plus 1 times the derivative of the top, 3u squared, minus the top, u cubed minus 1 times the derivative of the bottom, 3u squared, all over u cubed plus 1 squared. All right, and again, usually, as we've said before, it's a good idea to clean up the top. In this case, you'll get quite a bit of cancellation, but don't bother multiplying out the bottom. But we can do a lot with the bottom. Okay, I've got 8 on top, u cubed minus 1 to the 7th on top. Now for u cubed plus 1, I have u cubed plus 1 to the 7th, right here. These two combined, u cubed plus 1 to the 7th. Here's another u cubed plus 1 squared. So that's a grand total of u cubed plus 1 to the 9th. Okay, so u cubed plus 1 to the 7th, u cubed plus 1 squared, so to the 9th. There's 8, u cubed minus 1 to the 7th. Okay, now what about all this junk right over here? I factored out the 3u squared, and I'm left with, let's see, sorry, this should be u cubed. Fortunately, they cancel out anyway. U cubed plus 1 minus u cubed plus 1. Okay, the u cubes cancel out. I have 1 plus 1, which is 2. Okay, so one more time. Factor out the 3u squared. I have u cubed plus 1 minus u cubed minus a minus 1, so that's a plus 1. Okay, so the u cubes cancel out. 1 plus 1 is 2. 2 times 3 times 8. 2 times 3 is 6. 6 times 8 is 48. So final answer is 48 u squared, u cubed minus 1 to the 7th, all over u squared plus 1 to the 9th power. And I think that's just a smudge there. So maybe I'll change it into a plus, just so there's no confusion there. All right, so that's it for that one. Okay. All right. 27. R of t is base 10 2 to the radical t. So here's our first instance of not having base e. It's base 10. So from what we said over here, I'm going to have 10 to the blah, 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 ln 10. You see, it's a lot more difficult than if you have base e. So that's why we frequently say in calculus, we like base e. We don't like any other bases. Okay, so you might think, oh, we're a lot more comfortable with base 2 and maybe a lot more comfortable with base 10. In calculus, no. The easiest base is base e. The derivative of e to the x is e to the x. If you have any other base, a little bit more difficult. What's the derivative of 2 to the x? 2 to the x ln 2. What's the derivative of 10 to the x? 10 to the x ln 10. Okay, so this one, I'm going to have to put an ln 10, but I'm not even done with what I need already here. So 10 to the 2 radical t. Now think of it as 2t to the 1/2, right? Radical t means that. All right, so first you've got 10 to the radical t ln 10. Okay, so that ln 10 comes from this law over here. Okay, so 10 to the 2 radical t, derivative is 10 to the 2 radical t ln 10, but now it's times, I messed up there, times the derivative of the exponent. So I have to differentiate 2t to the 1/2. So what's the derivative of just this? Focus only on that. 1/2 times 2 is 1, t to the negative 1/2. All right, so I have t to the negative 1/2, and by rules of algebra, that negative goes in the denominator as a square root. So here's the best final answer. 10 raised to the 2 radical t, ln 10, all over radical t. All right, so that's that. I was going to hold off on these others until tomorrow. Okay, so I'm basically done. I'll blab for maybe 2 more minutes, and then I'll let you ask questions. So if you have any questions ready, be ready to bring them up. Okay, but what's going to happen tomorrow? Let me show you weird-looking stuff like 31. I was going to do that tomorrow. E to the t sine of 2t. If you can't read that, t sine 2t. So here's a chain rule, but inside the chain rule, there's a product rule and another chain rule. Because somewhere you have to differentiate t sine of 2t. So that's a product rule. There's going to be another chain rule there also. Okay, the other thing I want to mention is you might have to go more than 2 deep for your composition of functions. Right now, we've just considered f of g of x. Okay, we might have several layers. Let's look at 39. There are 3 levels here: tan, secant, cosine. I'll show you that tomorrow. But first you say, okay, the outside function is a tangent. So you would go secant squared of all this, and then times the derivative of the inside. Okay, so you're done with tangent. The inside is a composition in itself. You have secant times cosine. So you would go secant tangent times the derivative of the inside, and the derivative inside is another function, cosine. Okay, I'll show you tomorrow. 45 is really a doozy. Look at 45. Y equals cosine square root sine tan pi x. So there are 1, 2, 3, 4, 5 functions deep. So the chain rule goes 5 deep because your outermost function is the cosine. Second is the square root. Third is sine. Fourth is tangent. And fifth is multiplying by pi. So you have cosine of blah, blah, blah. You would do negative sine of all that. Then once you're finished with that, you have to differentiate the square root. Then after that, you have to differentiate the sine. Then after that, you have to differentiate the tangent. Then after that, you differentiate pi x. Okay, so there's a lot going on there. And I'll show you that tomorrow. I've just given you a little taste of it, how that's going to be. Okay, but for now, I'm pretty much done. So tomorrow on the schedule, I'll do some more of this. Let's see, where are we? We're way over here. Yeah, so I'm right on schedule. I'll do some more 3.4, but I'll introduce 3.5, which is something called implicit differentiation. Implicit differentiation. I have Tuesday and Wednesday for that. Okay, but I'm done with what I was going to share. So let me stop the share and check the chat. And I got an empty chat. Okay, so it's only 12:45-ish. Let's see. So now we see some 3.3 number 7, 3.3 number 43. Okay, so let me see what that is about. Okay, 3.3 number 7. And 3.343. Let me make a note of myself. 243 also. And 3.229 was asked for. Okay, so let me see if I can get these out of the way first. Okay, 3.3 number 7. Y equals C cosine of t plus t squared sine of t. Okay, C is a constant. Pretend it's 7 or something like that. So derivative of cosine is negative sine, so negative C sine t. And this is a product rule. First function, second function. So first times the derivative of the second plus second times the derivative of the first, which is 2t. So negative C sine of t plus t squared cosine t plus 2t sine of t. Okay, 3.343. Let's see, limit x approaches 0. Sine of 3x. I'm going to write it funny like that. 5x cubed minus 4x. Okay, so we said the name of the game is to make this thing have exactly something like that in the bottom. So I divide top and bottom by 3x like that. Okay, the limit of a quotient is the quotient of the limits. That means write it like this. Limit x approaches 0, sine of 3x over 3x over limit x approaches 0, let's see, that comes out to be 5/3 x squared minus 4/3. And there we go. Again, as x approaches 0, so does 3x. Okay, so this whole thing is 1. This thing is 0. So it looks like I have 1 over negative 4/3, which is negative 3/4. Okay, so again, divide top and bottom by 3x. In order to use that theorem, okay, this angle has to match that, so I divide by 3x. So that would then split it up. So this becomes 1, that's 0. So 1 divided by negative 4/3 is negative 3/4. Okay, 3.229. F of x is x squared over 1 plus e to the x. And they want the second derivative. Okay, quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom. Derivative of 1 plus e to the x. Derivative of 1 is 0. Derivative of e to the x is itself. Over 1 plus e to the x squared. And now let's clean it up a little bit. 2x plus 2x e to the x minus x squared e to the x. It might be easier to factor out the e to the x before I take the second derivative. 2x plus 2x minus x squared e to the x all over 1 plus e to the x 20 squared. And now I have to find y double prime. So, okay. Let me do the easy part. I'm supposed to square the denominator, right? So I have 1 plus e to the x squared. That means to the 4th power. Okay, so now it's bottom times the derivative of the top. So I copy the bottom. Times the derivative of the numerator. Okay, derivative of 2x is 2. Plus, and right here, I got a product root. So there's a product root inside a quotient root. So first times derivative of the second. Derivative of the second is just e to the x. So that part I'm just going to copy. Okay, plus the second function, e to the x, times the derivative of the first. Derivative of this is 2 minus 2x. Okay, all of that was bottom times the derivative of the top. Minus the top, may not have enough room here, 2x plus 2x minus x squared e to the x, times the derivative of the bottom, and I painted myself in the corner. I'll have to sneak it here. Okay, how do I differentiate this? Okay, well, now that we have the chain root, I'll just sneak in the chain root. It's 2 times 1 plus e to the x times the derivative of the inside, which is also e to the x. So you can see it's a big mess, okay, which I'm just going to say, etc. And if I give you something like this, I would just have you stop there. But, I mean, it's a lot of very messy algebra, but that's essentially the second derivative right now. Okay, so the first derivative wasn't so bad, but the second derivative was. So I'll just speak to it quickly. So I copy the bottom times the derivative of the top, but the top involved a product group. So copy the bottom. Derivative of the top, derivative of 2x is easy, but the derivative of this was not so nice. First times derivative of the second. Fortunately, I was taking the derivative of e to the x, so it's itself, plus the second times the derivative of the first. Derivative of this is 2 minus 2x. Okay, all of this, everything up to here, is bottom times the derivative of the top. So it's minus the top. So this stuff, I copied the original numerator. And then times the derivative of the bottom. So chain root, I bring down to 2, 1 plus e to the x times the derivative of the inside. Okay, and I'll just leave it like that. Okay, so stop the share there. Check 3.3 number 7. Why don't you have to apply a product rule for c cosine t? Okay, so number 7, the c is a constant, so it's a constant multiplier rule. Okay, so c is a constant. It's just like 7 cosine t. It's 7 times the derivative of cosine. Okay. And let's see. How do we know? That has to be understood from the problem. Okay. When it's given t is the variable for something like that, and we have to understand that c is considered a constant in that kind of a problem. Okay. So normally, if they don't tell you stuff like that, I would tell you, but usually A, B, and C are not variables now. They're meant to be constants. T is going to be a variable. X is a variable. Okay. Yeah, technically, I guess you could count it, but you would just have to know from experience from something like this that the C is meant to be a variable here. C is a constant here, and T is a variable for something like 3.3. Let me check something out there. 3.3, number 7. Yeah, I think I may have said it earlier, but yeah, let's see. Shouldn't C be 0 for question 7? C is a constant. It could be 7, but you normally don't want to think of it that way. Its derivative is 0. Yeah, but that's irrelevant here. Let's see. I still have time. Let me go ahead and show that. But what Prasanna has is correct also. Okay. So here, C is a constant. If it helps, pretend it's temporarily 7 or 3 or pi. Okay, so it's a constant multiplier rule. So the derivative is C times the derivative of cosine. Derivative of cosine is negative sine. So it's C times negative sine of t. Okay. The derivative of C is 0. Yes, that's correct. If you wanted to talk about that technically. Okay. All right, I think we're caught up with the chat there. So anybody else? Otherwise, we're done for the day. And yeah, anytime when I'm lecturing, if you want to type something in the chat, and Prasanna can get to it also, you can do it. So thanks a lot, Prasanna, for helping there. Okay, that's about it. All right, so we're done. Tomorrow I'll do a little bit more of these type of problems and then get started with the next section, 3.5. All right, that'll do it for today, folks. So everybody have a good afternoon, and we'll see you next time. Bye.